For as long as we've built things, we've known one thing about concrete. It's strong, it's rigid, and it doesn't bend. But what if I told you that its greatest strength, that rigidity, is also its fatal flaw? Well, today, we're diving into a material that flips that entire idea on its head. A concrete that's been engineered right down to the molecular level to do something that sounds impossible, to bend without breaking. And this gets to the heart of a really big question in civil engineering. I mean, think about it. For over a century, we've been on this relentless quest to make concrete stronger and stronger. So why is it that our bridges, our roads, our buildings, they all still seem to crack way too soon? What have we been missing? All right, to really get to the bottom of this, we've got to look at how we got here. The story of concrete is pretty fascinating. It's this constant push and pull where every time we solved one problem, we kind of accidentally created a new one. So let's take a quick look back. In the 50s, a basic 30 or 40 megapascal concrete was plenty strong. But then, fast forward to the 70s and 80s, we're in this race to build higher and higher, and suddenly we're pushing past 130 megapascals. But then a funny thing happened in the 90s. We realized all these super strong structures were still falling apart. So the focus shifted to durability. And more recently, of course, it's all about sustainability. Every step made sense at the time, but it was leading us somewhere unexpected. And this is where it gets really interesting. Researchers Mehta and Burrows pointed out this massive paradox. It turns out the more we jacked up the early strength of concrete, the less durable it often became in the long run. It's a total catch-22, right? The very thing we were doing to make our structures last was actually making them fail faster.
So what gives? What is this hidden flaw that's been tripping us up for so long? Well, the answer is a fundamental imbalance that's literally baked into the nature of concrete itself.
Okay, this slide right here, this is the whole story. As engineers, we obsess over compressive strength, how well concrete resists being squashed. And it's amazing at that. But try to pull it apart, even a tiny bit, it's terrible. And guess what causes most real-world failures? Shrinkage, thermal stress, seismic events. They're all failures in tension. We've been focusing on the wrong thing, ignoring its Achilles heel. And that brittleness, that tendency to just snap, is the ultimate bottleneck. It's what holds us back from building truly resilient infrastructure. It compromises durability, and let's be honest, it kills sustainability because brittle things need to be repaired and replaced all the time. But what if we could just change the rules? What if instead of chasing strength, we started chasing toughness? What if we could tackle that tensile weakness head-on by redesigning concrete from the inside out? Well, that exact line of thinking led to a whole new class of material. And here it is, meet engineered cementitious composites, or ECC. And that first word is the most important one, engineered. This isn't just a new recipe. It's a material designed with micromechanics, where every component, the fibers, the matrix, the bond between them, is fine-tuned for one specific goal, ductility. It's designed to behave less like a brittle ceramic plate and more like a ductile piece of metal. Now, if you're a numbers person, this chart says it all. We're looking at tensile strain capacity, basically how much a material can stretch before it snaps. Normal concrete, it's that tiny little sliver at 0.01%. Even fancy ultra-high-performance concrete, UHPC, only gets to about 0.2%. And then you have ECC, way out in a league of its own, at over 2%. Yeah, you're seeing that right. That is over 200 times the ductility of the concrete we use every day. 200 times more give before it fails. This isn't just a small improvement, this is a complete paradigm shift in material science. It's a game changer. So how does it pull this off? What's the secret? Well, when you overload regular concrete, one big crack forms and it's game over. ECC is way smarter. It's designed to spread that stress out, forming a network of thousands of tiny, controlled microcracks. The fibers inside bridge these cracks, allowing the material to actually get stronger after it starts cracking. It fails gracefully instead of catastrophically. Okay, so when you have a material that is this different, you can't just drop it into the old way of doing things. It doesn't just allow for a new design philosophy, it demands one. For decades, the process has been completely disconnected. It's like an assembly line where the departments don't talk. The materials people cook up a concrete mix based on a strength number. They hand it off to the structural engineers, and everyone just kind of crosses their fingers and hopes it lasts. Its actual performance over time is just an afterthought.
ECC lets us smash those silos. It opens the door for a truly holistic approach called ISMD, Integrated Structures and Materials Design. And it's all about creating a conversation between the material, the structure, and what we actually want it to do in the real world. And this feedback loop is just brilliant. Instead of starting with the material, you start with the end goal. You say, I want a bridge deck that lasts 100 years. And then you work backwards. That goal tells you the structural behavior you need, which tells you the material properties you need, like high ductility. And with ECC, you can actually go back and engineer the material's microstructure to deliver exactly that. You're connecting the nanoscale to the megastructure. It's a complete flip of the script. Now, this all sounds great in theory, but is it just a cool lab experiment? Absolutely not. ISMD and ECC are already out there in the real world, solving some of our most difficult infrastructure problems. We're seeing it used for all kinds of things. Think about highway patches that don't fall apart after one winter, or expansion joints on bridges that can actually flex with temperature changes without failing. In earthquake-prone areas, it's being used in high-rises to build beams that can absorb seismic energy. It's proving itself everywhere, from simple repairs to brand-new cutting-edge construction. So the big takeaway is this. The greatest innovations can come from identifying a material's most fundamental weakness and completely re-engineering it from the ground up. The journey to bendable concrete is incredible, and it leaves us with a really provocative question. If we can teach our oldest, most stubborn building material this amazing new trick, what other materials are just waiting for their own redesign?